Now, we're going to take up one more problem on shafts. The problem number 10, it reads as a steel shaft is to be manufactured either as a solid circular bar or as a circular tube. The shaft is required to transmit a torque of 1200 Newton meter without exceeding an allowable shear stress of 40 MPa, nor an allowable rate of twist of 0.75 degrees per meter. The shear modulus of elasticity of the steel is 78 GPa. Now, the problem, we have to see the data. So first, what we need to do is determine the required diameter D of the solid shaft and determine the required outer diameter D2 of the hollow shaft if the thickness of the shaft is specified as 1/10 or 10% of the outer diameter. And C, determine the ratio of diameters, that is D2 by D, and the ratio of weights of the hollow and the solid shafts. So the data given is the torque, which is 1200 Newton meter, which will be equal to 1200 into 10 to the power of 3 Newton mm. Then he has given the allowable shear stress tau is 40 MPa, which is equal to 40 Newton per mm square, and theta is given to be 0.75 degree per meter, which will be equal to, converting into radians, 0.75 into pi by 180 will be equal to that, whatever the value, which will be in terms of radians. And G, which is equal to 78 GPa, which is equal to 78 into 10 to the power of 3 Newton per mm square. Also, the theta is given for 1 meter length, so take L will be equal to 1 meters, which will be equal to 1000 mm. Now, first we're going to find out what will going to be the diameter of the solid shaft. So based on the strength criterion, so here T equals pi d cube by 16 into tau. So after substituting T by Jp is equal to tau by R. So from there, you will going to get it as Jp by R into tau, where Jp by R is Zp. Zp value is pi d cube by 16 into tau. So we have substituted directly that particular formula. Therefore, the torque, which is 1200 into 10 to the power of 3 divided equals pi d cube by 16 into tau is 40. So therefore, the diameter of the shaft is 53.46 mm. Then based on the torsional rigidity or stiffness, which is T by Jp is equal to G into theta by L, which is T is equal to Jp into G into theta by L, where J will be equal to T into L by G into theta. So pi d to the power of 4 by 32 will be equal to T, that is 1200 into 10 to the power of 3 into the length is again 1000, 1 meter. So 1000 10 to the power of 3, that is either 1000 or 10 to the power of 3, divided by G, which is 78 into 10 to the power of 3 into 0.75 into pi by 180, which is converted into radians. Therefore, the diameter of the shaft is 58.82 mm. So the permissible value is the maximum diameter is the permissible among two values or bigger among the two values. Therefore, adopt the diameter of the shaft D will be equal to 58.82 mm or 60 mm. Then considering the second part, which is the second part of the problem, which is B, outer diameter of the hollow shaft, if D1 will be equal to D2 minus 2 into 0.1 into D2, which is equal to 0.8 into D2. So based on the strength criterion, again T is equal to pi by 16 into D2 to the power of 4 minus D1 to the power of 4 divided by D2 into tau. So that is 1200 into 10 to the power of 3 by equal to pi by 16 into 40 into D2 to the power of 4 minus 0.8 to the power of 4 into D2 to the power of 4 divided by D2. So on simplification, 1200 into 10 to the power of 3 will be equal to pi by 16 into 40 into d2 cube into 1 minus 0.8 to the power of 4. On simplification, you will going to get outer diameter of the hollow shaft, which is d2, which is 63.73. Based on the torsional rigidity stiffness or torsional rigidity, T will be equal to J into G into theta by L, where J is equal to T into L by G into theta. So substitute J will be equal to pi by 32 into d2 to the power of 4 minus d1 to the power of 4, which will be equal to 1200 into 10 to the power of 3 into 10 to the power of 3 divided by 78 into 10 to the power of 3 into 0.75 into pi by 180. That is pi by 32 into d to the power of 4 into 1 minus 0.8 to the power of 4, because d1 by d2 will be equal to 0.8. So 0.8 to the power of 4, which will be equal to 1200 into 10 to the power of 6 divided by 78 into 10 to the power of 3 into 0.75 into pi by 180. So on simplification, outer diameter of the hollow shaft d2 will be equal to 67.1 mm. The permissible diameter of hollow shaft, that is G2, will be equal to 67.1 mm or approximately 70 mm. So then what we need to do is to find out the third case, wherein ratio of diameter D2 by D and the ratio of weights. So ratio of diameter D2 by D will be equal to D2 is 70 by, that is 67.1 divided by D, which is 58.82. On simplification, you will going to get it as 1.14, the ratio. Similarly, for same material and length, weights of the shafts are proportional to their cross-sectional areas. Therefore, the weight of the hollow shaft divided by height of the solid shaft, which is WH, capital WH by capital WS, will be equal to pi AH by AS, which will be equal to pi by 4 into D2 minus D2 square minus D1 square divided by pi by 4 into D square. So that is equal to D2 square minus D1 square by D2. So substitute the values of D2, D1 and D, that is 67.1 the whole square minus 53.68 the square divided by the diameter is 58.82 square. So on simplification, you will going to get it as 0.4685 approximated to the ratio as 0.47. Therefore, D1 will be equal to 0.8 into D2, which will be equal to 0.8 into 67.1, which will be equal to 53.68 mm. So these results shows that the hollow shaft uses only 47% as much material as it does the solid shaft, while its outer diameter is only 14% bigger. So this is how you will be able to analyze and solve this particular problem. Thank you.